All right, so to start with, let's talk a little bit about some of the issues that we'll be dealing with today, right? So this idea of looping. So probably, at this point, you guys have had plenty of experience working in Grasshopper, and you may have on occasion run into a situation in which, you said, well, wouldn't it be great if I could take this polygon that I created and then put it in, let's say, here, right? I mean, it's a polygon, it's a curve, right? So why can't I put in this curve container, right? Um, so the tricky thing about this is that what you've just done is you've created a kind of loop, right? And so, parametric design by nature has kind of has a one directional flow, right? So the things that you did earlier on happen step by step procedurally, right? So the things that are later on in the chain, right, are, the kind of earliest things in your history, right? Now, the problem is if you take something that is generated farther down the line, let's say, this line, and you try to plant that somewhere earlier on in your definition, right? Let's say we put it here, right? Your definition will fail, right? And the reason, it's a little bit like traveling in time, right? Because now you're trying to use the result that you got as an input to the same definition that gave you that result, right? Which, if you think about it, makes a lot of sense, right? You can't have this result and then feed it into here if you didn't already have it run through once, right? So, but there are times actually where it seems like that's what you want to do, specifically if you're working on things that require a kind of iterative process, right? To go kind of run through that process over and over and over and over again, right? And it's quite limiting in Grasshopper to only be able to have your work go in a one directional flow, right? So everything we're going to be talking about today is about addressing that issue, right? So let's go ahead and get started, and we will set up our initial example to explore this idea, right? So the first thing I want to do is let's go to the website and let's look at fractal. Right. So a classic example of something like this is the kind of mathematic phenomenon of fractals, right? So if you look at a fractal, let's just look at some pictures since we're graphically oriented, right? You can start to understand how some of these things are, generated using the same description, right? Every single one is the same, but for each iteration, right, it kind of grows on the next one, right? So, for instance, this hexagon growing on itself, the triangle growing on itself, right? And the phenomenon of trees, right? So today we're going to use a tree as an example because I've done it before. And, you can kind of see how, well, each generation, right, is the same as a generation after it. And after, 1, 2, 3, that looks like it's, growing ridiculously fast, but you have to remember that it's an exponential growth, right? So every generation is exponentially bigger than the one before it, right? So after 6, 7 generations, right, it's huge, right? And wouldn't it be convenient to just have to write that definition once instead of writing it once, feeding this result into here, and then feeding this result into here, and then feeding this result into here? It's quite tedious, right? So if we were able to implement a kind of looping feature within our definition, right, that could record each instance at each generation, then in fact, that process could be quite fast, right? So the first thing, though, we're going to do is we're going to set up the kind of base condition, right? So if we're talking about, tree branching, right, then we're really looking at just, lines that split, right, into, more than 1, 2, 3, or 4 additional branches, right, before starting a new generation, right? So let's just set up that kind of basic requirement, right, which is to have a line that splits with some amount of control so that we can play around with the geometry a little bit at the end, right? So at this point, this should be all very easy for you guys. So we're going to start off with an SDL line, right? And we will define that using world XY plane as our starting, a length and a direction, right? So let's say length, we start with 0 to 10, and a direction, we will use a unit Z. As our starting, right? So there we have our line. Now, there are lots of different ways that you can go from here. If you wanted to, say, draw branches that start kind of moving away from our, our single stem here, one way to do it is to kind of draw an offset of a polygon, right? And that would be very convenient because it would also allow us to kind of define how many branches we want at the same time, right? So let's go ahead and do that. I'm going to go and choose under curve, primitive polygon, right? And the location of this polygon, I will define, in relationship to the initial line, right? So again, by default, the plane will be the world XY, but we will want to define that on our curve somewhere, right? So to do that, right, it makes sense that we are using our curve, or is it be under transform orient? Horizontal frame, I think. So with our horizontal frame, what we're going to do is we're going to input our curve, right? And what this allows us to do is place our polygon on this line, right? At a certain parameter, right? So if this line has a 0 to 1 relationship, right? We talked about parameters before. That means we can define that using a slider between 0 and 1, right? So you can see now I can very easily place this polygon on that line anywhere we want, right? Okay, so the next step, right, is that we want to have some flexibility in terms of how our polygon affects our design. So right now we have 6 segments, right, which means that, for instance, if I were to draw branches, right, each one would come off into one of those corners. I want to be able to change that though, so I'm going to define it using a slider here, right? And that way I could increase or reduce quite dramatically, right? I'd also like to be able to change the size, right? And I think that that's enough function. The fillet radius I don't think is useful for us in this case because, it doesn't matter that we have rounded corners or not. Actually, we want those corners. So I think for that component, we really just need those two parameters to be flexible for us, right? Okay, so now that we kind of have a starting point for our, say, first part, what about drawing the actual branches themselves, right? So actually, before we get started, I want to mention something about this, right? Maybe some of you will probably wonder why I didn't go back and use a point on curve, right? Which was here somewhere. This one, right? The one we used before, which would allow us to place that point along this curve, and that could have easily served as our starting plane for the polygon, right? I mean, the difference between these two are pretty subtle, right? They basically work the same way, except that using a horizontal frame, right, will allow us to not only have the positioning, right, but the orientation, right, of this polygon related to that line, right, which is not so important in this first generation, but further down generations later, you will see that because as we branch off, we may not be branching off at, 90-degree angles and directly, in the Z axis, right? We're going to be working off several angles. And so using a frame is going to be important for us at that point. So, and it doesn't hurt us now either. So we might as well just do it. Okay, so the next thing is to kind of, develop our line, right? And so what I want to identify a starting point for the line that's drawn, right? And on this example, we can just either take, the one of the two ends basically. And I think if we're talking about a fractal tree, right, it makes sense that it's at the top end, right? So I just want to find now our endpoints. So I'm going to take my line. You can see that the two endpoints are discovered. I don't yet know which one is the one I'm interested in because I'm not sure what the directionality of that line is, but we'll know in a moment, right? Okay, and then so the first thing that you're going to think is going to be straightforward, right? That we can just take the discontinuity, right, from our polygon to create these points. And the number of those points, right, can be matched up to here by drawing a line directly, right? Let's say like this. And you can see that, that part identified as a start, and so we're actually interested in the end, right, to get the branches, right? And then of course, depending on the positioning of the polygon, we could control the angles, and that's all very straightforward. But except for one thing, right? Except for the fact that just like in our example below, where we had to consider what the situation would be, generations down the line, one thing that we have to keep in mind is that we will run into a similar situation, right, with everything else in our definition, right? So we're not going to be able to do it as simply as this, right? So we actually need to define a directionality to it as well. So for that aspect, we're going to use our vector components, and we're going to define a vector with an amplitude, right? So there should be a vector amplitude and a vector from 2 points. So the vector from 2 points, we're going to use our points from our line here, right? Let's say start was on the bottom and was B, right? So what that tells us, right, just as, it tells us the direction, right, that this line is going. And again, just like in the previous part, right, where we're talking about establishing the position of the polygon down here, it's easy to assume, right, because it's just going straight up in the Z direction, that's all we need, right? But again, further down the line, when this line gets replicated on, the ends of something else, right, it may not be, the vector direction may not be that straightforward, right? So what this allows us to do is analyze for the direction of that line, right, from the start and the end point, right, the 2 points, right? So I'm getting the vector as well as the length result, right, for now. The vector amplitude, right, what this is going to allow us to do is be able to modify the length to something that we want, right? So it gives us a little bit more control of what the result of our move will do, right? So I'm going to use a slider there as well. And I'm going to connect that to the amplitude. Right. So now this has some degree of adjustability. You can see point-wise it's 0, 0, 4, whereas by default, the vector was 0, 0, 10, right? Because this line that we used to establish the vector was 10 units long, as defined by the SDL here at 10, right? Okay, so now that we've actually established the directionality and the amplitude, right, we can use that to move, right, those points in the direction we want, right? So right now we have, these points established, but, they're kind of, if we were to imagine that the branches would grow up from here, right, it doesn't seem that natural for them to grow off, at a 90-degree angle, like a flat canopy, right? So we're going to want to be able to move them, a little bit away from this point, right? By a certain amount, basically. And that's what we're going to do with the amplitude adjustment, right? So we're going to use our move component under transform. I think I need more space. To take this geometry, right, and then define a motion for it, right? And the motion for it will be, a factor of this vector, right? Whatever our set vector is. And, as you've seen and as we've done before many times by now, what we can do to adjust this is simply use a mathematical function, right, as to define the size and amount of that movement, right? And that will allow us to have, some flexibility, right? So I'm going to take this vector, right? And I'm going to choose to use a slider between 0 and 1, right? So that's the default slider. And that will define the motion, right? Now, actually, this one is fixed here. It's controlled by this point. So I want to do the other one based on the length of this line, right? So that proportionally, it will always reference the length of the original line. So to do that, I need to figure out how long that line is. So we'll do a length analysis of this line. And then I'm going to use this line as the base. And that will serve as my motion. Now, okay, so I need these two, because right now what's happening is this is not a vector yet, and this is expecting a vector. So what I can do is I can move this down into my vector here. This geometry should actually be this polygon. Hopefully that makes more sense. There we go. So, so you can see all that really did was move this polygon away from the endpoint of that SDL line, right? And then again, that's going to be something that I can now adjust, using this slider, right? And this amplitude has effect on that as well, but we can leave that at the way it is for now. So now that I've actually done that, then now that makes more sense as my discontinuity point, right? Because now it's not going to be, flat, and I can adjust the angle at which I want the branching to occur using these amplitude adjustments, right? From there, I basically have my starting point, right? Now, let's clean this up just a little bit so that when we get to actually setting up the loops, we don't get too messy. Okay, so I'm going to hide everything and only show these objects that I am actually interested in. So all of that was basically just to set up this initial branching, right? And let's test the functionality. So you can see by changing the radius, right, I can change the angle at which they branch off at. Changing the number of segments, I can change how many branches appear from each element, right? Changing the parameter, you can see that that adjusts how wide, well, that again, it's the same as kind of the angle, but it doesn't impact the size and how wide those branches get. It just, changes how, let's say, how high those branches go. And then these adjustments, they allow you an overall control over how big, right, those branches and ultimately the tree will get, right? And this one overall is the length, right, of your starting branch. But again, because some of these are proportional, right, it will affect other things as well. Okay, so that's our base definition, right? So I'm going to go ahead and group this now so we can remember that as our starting point. Now, if we wanted to do another set, right, and they were going to grow out from the tips of those 3 branches, right, how would we do that? I mean, it's tempting to think that we can, okay, we'll take these 3 and we'll input it again, right, here. In fact, let's use a curve container, move these off a little bit. Right, it's tempting to think that, well, now that I have this result, can't I, put this into here, right? And then it will give me the next generation and the next generation after that. And the problem is that you can see that that's the looping error that we run into, right? And it's just that simply because we can't we can't go back and modify something from, what did I just do there? We can't go back and modify part of the past record, right, with something from the future, basically. Now, many of you would have thought, well, oh, okay, so we can't do that. Maybe actually what we could do is something like this, right? Copy and paste, right? And then we go like this, right? And then we have our, kind of next generation appearing up above that, right? And then we can just do another copy, another copy, another copy, right? But of course, that looks pretty messy, right? And, just doesn't seem like a great strategy overall, right? Conceptually, there's nothing wrong with that, though. And I think it's a good opportunity now to introduce you guys to something called the cluster, right? Because at least using clusters, you can kind of neaten up your canvas while achieving the same thing. But maybe before we move on to that, let's give everyone a little time to set this up first. And then we'll go ahead and discuss the way that clusters work in Grasshopper. Okay, so looking at clusters now. So what we were trying to do just now was actually take this as if it were, a single component that was doing one action for us, right? And there is actually a way to write your own components, this using clusters, right? And so let's look at that quickly before we move on. So under our parameters tab in utility, we haven't looked at these ones much, but there's something called a cluster input and a cluster output, right? So the cluster output is whatever comes out of your definition, right? So in this case, it's going to be, some lines. And the cluster input is essentially all the different components, right, that are required to make your definition work, right? So here we can say, well, we need to inherit whatever curves are important, right? We also need then to have something for the control of the amplitude, right? And don't worry about things starting to fail, right? That's fine. We're going to need to have something for the control of the frame parameter. We're going to need something for the radius. And we're going to need something to set up the segments, right? So those are essentially our control elements, our main control elements. So you can see here, we left this one out in a way, simply because the amplitude does almost the same thing in this case. So we'll just leave it like that. And these ones are customizable, right? So you can rename them, right? And depending on how you name them, you will get a different result for, it'll just give you a different name for the input, right? Right now, all of these are kind of the default ones, but let's say radius, right? We could rename that as spread. Really, the nickname is the only one that appears. Segments, branch, number. All right, so that's essentially the number of branches that you want to grow. Parameter, which is pretty vague, right? We can change to position. Amplitude, maybe that's fine. And then the base curve is just the input curve, so I don't think we need to modify that at all, right? So now that we have all of our inputs parameters set up and we have our output parameter set up, we can select everything, right click, and actually middle click, and then choose cluster. So you can see here, essentially what you've done is you've just created your own custom component, right? So, again, you can do this for anything that you write, right? So you can start to imagine like all of these plugins that people are making, right? Actually, all they're doing is kind of writing their own definitions, putting it into a cluster, right? And then, repackaging it for someone else to use, right? So now we happen to have a component that will draw, branches, for instance, right? Essentially. And you can change if you want your icon, right, to whatever you want just by going into the properties tab. And that's essentially it, right? So once I get to this point, though, you can see I can just now copy and paste the starting curve, right? I'll just use this. And I will still need some sliders, right, to modify those 4 parameters, right? And, they're more or less going to be these 4. So amplitude, position, spread, and branch number. Hide this so it doesn't get confusing, right? So that's essentially the same as all of this, just packaged more neatly, right? So you can see now if I change my amplitude, right, it's working. I can change the position. It's fine. I can change the spread, and I can change the number of branches, right? So as well as the length. Okay, so that's the starting point then. And now, just like we did before, if we wanted to kind of continue to develop, we can just say, well, I'm just going to run this component over and over again then, right? And you can see 1 generation down, 2 generations down, right? 3 generations down. Oh, not exactly what I expected. Okay, so it looks fine kind of in the first generation, the second generation, okay, and then bunching up here. Okay, so I have a data matching problem, I think. So let me get rid of this. I need to modify the original first. So here, I guess this one I need to graft, right? Because we have only 1 point here, and then we have, 3 points here, right? But after each generation, right, these points grow much faster than these points. So if I graft it, that means it'll force all of these to match to that one, regardless of the size of the list, right? So that's back to our data matching stuff. So now that I've modified that, let's see if this component is now working. Yeah, that looks better already. Okay. Yep. Good. Yeah, you can see the list structure changed after the second generation here, right? And that's why if I didn't graft it, then the matching of the lists probably wouldn't have worked out correctly, right? But this looks much better, right? So here is our diagram, our fractal diagram, right? Which is a tree growing out with 3 branches at each generation, right? So 3 there, 3 there. And again, it's, doing a good job of kind of maintaining the directionality, right, at each point, right? And if I come in here, I start to modify like the size and the shape, you can see that, we can, all of those different characteristics carry through. Spread and, oh, yeah, number of branches. So you can see like if we had, 5 branches at every generation, how quickly and how dense that becomes, right? One thing to be aware of, I think, is that, when you're working with loops, you need to be a little bit careful because as you can see here, this is pretty slow because we're still just copying 1 generation at a time. But if that's an automated process and you accidentally did like 10 generations instead of 6 generations, the difference between generation 6 and generation 10 is probably your computer crashing or not crashing, right? So, just be aware that when you're working with stuff like this, processing, changes dramatically with each generation above a certain amount, right? Okay, so this is, of course, another strategy you can take is by using clusters, right, to make this a function by itself, right? And you can, again, this is useful in this instance because it saves us, a big mess of a definition, right, to try to maintain. But It's also useful to be able to understand how to use clusters for lots of other tasks that you're working on, right? Particularly as as your definitions get more and more complex, you'll be looking for ways to more efficiently use your workspace, right? Okay, so next we will look at a plugin. So we'll talk quickly about how to install the plugin, since this is your first time, probably for most of you. And then we'll do the same example using new components provided by that plugin. Okay, so the plugin, or where you'll find most plugins for Grasshopper, is at the website called Food for Rhino, right? I believe I've introduced this site to you guys before, but it's a invaluable resource for anybody working in Grasshopper. So, after a certain while, you have enough experience with Grasshopper, you start to run into certain situations where, you wish there was, more functionality so that you could do this or that, right? Especially those people who are working in meshes, you probably found out very early on that, the kind of base Grasshopper component set that we've been, looking at this whole semester here, right, had, fairly limited mesh tools, right? And of course, that's, to some respect, that has to do with the characteristics of the geometry itself being so simple, but it also has to do with the fact that Rhino, was never a mesh modeling software. So, it wasn't considered to be, particularly important at the time to have lots of different mesh modeling components, right? That, of course, has since changed. And what you'll find is that you can find lots and lots of different plugins now that are dedicated to expanding mesh functionality, right? And again, that's just one example. If you go into, for instance, now we clicked into the Grasshopper plugin section, you can see that there's officially 679 different plugins that are available to you with all different sorts of added functionality to Rhino and Grasshopper. And so on the right, you'll have a list, right? And this is, they're sorting by rating, right? You can also sort by all different methods, downloads, and you can still find the old version of Kangaroo before it was kind of incorporated into Grasshopper, and example, mesh edit, right? And Anemone, right? This is the one that we'll be looking at today, which is addressing the issue of kind of a linear workflow and wanting to be able to work on definitions that include recursion, right? Or looping. So, by chance, if you don't see it here, you can also search for the specific plugin using the name. Oops, I spelled it wrong. Oops, how do I spell that again? Oh, Anemone, this one, right? And it will pop up. And then you can click in. And then what you'll find is that, this will have a number of downloads available for you in most cases, right? And, it has kind of a recorded history of all the different versions, right? Partly that's because, some people running on older versions will only be able to use certain things, right? But as you can see, right, if you're running, Rhino 7, right, there should be no problem downloading the most recent version, right, with the most functionality, right? So when you hit the download, what typically will happen is that you'll get a component, right, or a zip file, right? In the case of Anemone, it's just a component. It doesn't require a zip file. And you can see here, it's this one called Anemone1 GHA, right? Now, if you got a zip file or any kind of components, what you need to do before you try to install it is to go to your Properties tab and make sure under Security, General and Security, you hit the unblock, right? Unblock and apply, then okay, right? That applies to your zip file as well as any other files that you've downloaded and that you're trying to add to Grasshopper, right? If you don't do that, the file, Grasshopper will not be able to read that file and will not detect it, right? So make sure that you do that important step. Now, in some cases, some plugins that you download will actually give you a download install file, right? And you can just install it directly and you won't have to worry about unblocking it, right? So here you can see under File and Special Folders, there's one called Components, right? And in most cases, what you need to do is you need to drop that component into the folder that opens, which, even though it's called Special Components, is, inside your system called in Grasshoppers and then libraries, right? I don't know why, but just put it in there, right? You can see that on my setup, I have the Anemone plugin already placed in that folder. Once you've done that, you restart the Grasshopper, well, Rhino and Grasshopper, and you should have added tab up here, right? So you'll see there's a tab now for Anemone, right? And again, I have additional tabs here because I have downloaded other plugins, right? You probably, yours probably ends at display. But in the Anemone tab, you'll find a number of components here that allow you to essentially use that a looping function, right? And, just as if you remember in Kangaroo, they had like all different types of solver. One is like a fast solver, one is a bouncy solver, one is a step solver, and one is like an animation solver. It's just a different effect, right? And so again, the classic solver, right? I think this is like an animated solver. This is a little bit, just some functionality, right? If you're using, for instance, I don't know, password or timer buffer, I guess that's for animation. You can choose, whichever you like. Essentially there's really only two components for each type of solver. We're going to use in our example the fast loop start and end, right? Just because it's, faster and doesn't require any additional processing, which is kind of important, I think, in most looping situations because, the file very easily gets pretty heavy, right? So we're going to take the start loop and end loop, right? And, it's pretty straightforward the way that this is going to work, right? So with the Anemone component set up, all we need to do is take our original starting line, copy that. We're going to use a container. And this container is going to allow us to cycle data, right? So if you look at the components here, there's a couple things to be aware of, right? There's this arrow here, right? And this essentially establishes the loop between the start and the end, right? So you can imagine it like, oh, it's going to send information this way through whatever definition you make. And then the data from that is going to be sent back here, right? It's going to output something at that point, and then it's going to send it back to process again, right? And that's like that looping, the sense of looping back into an earlier point of our definition, right? And there's a couple things that you have iterations, right? So for instance, when we say iterations, we may be 1 iteration, 2 iteration, 3 iterations, 4 iterations, right? So how many times you want that loop to run, right? And you can also do things where you have like conditional entry or exit, right? So there's a counter here, and when it reaches a certain amount or whatever, you tell it to exit, right? In which case it exits out of the loop, right? So, and essentially this part that says data is simply, well, okay, I'm going to input my starting data, which is just that line, right? And then I'm going to process that data with, let's say, the component that I created, right? You could also, put this whole thing here as well if you wanted to. But you see, I'm just going to connect the line here. I could have copied with these guys. Yeah. So the data will send this way. Take these ones here. Right, so this is the definition you wrote, and it's going to process. When it processes 1 iteration, if it completes 1 iteration, it will send the data out, which gets recorded here, right? And you can see the results, right? And so here's where the final thing is the number of iterations. Now I'm going to keep it 10. Am I brave enough? Let's start low, like 2. Okay. So you can see that now when I run it, there's 0th generation, right? The starting point where it's basically passed through once. 1st generation, 2nd generation, 3rd generation, 4th generation, 5th generation, and 6th generation. That's looking already pretty scary. So I'm gonna limit this to say 6 generations. I'm going to reduce my branch count, right? To say 3. Adjust my spread. Maybe increase the amplitude. Or not. Okay. And you're going to ask, well, that's great, but I'm only seeing 1 generation at a time, right? And so the way you address that is you come in here and you say record data. And when it's in record data mode, you can see that it will now show you every single generation that you've generated, right? And so essentially, that's how you would set up a loop in Grasshopper using the Anemone plugin, right? Pretty simple and straightforward. So, okay, why don't you guys try that on your own, and then we'll talk, a little bit about our last week or 2 of class before we end today's session.